Hello, the internet. So today we are going to be continuing our conversation about MO theory by building up a description of overlaps in between atomic orbitals that get a little bit oblique. It's time for pi bonds. So previously we've looked at the overlap in between s or pz orbitals. This time we're going to start by building up the overlaps in between sets of px and py orbitals. So by convention, right now we're using the 2px and 2py, but you can extend this idea to 3px, 3py, 4, 5, all the way down the periodic table. So when we do this, we have our classic trick. We can make symmetric or anti-symmetric combinations. However, here we like talking about symmetric combinations first. So we're going to build up our set of pi bonds by doing the symmetric combination of either the px or the py orbitals, atomic orbitals, on atoms A and B. So again, these two will add up separately because it's going to be hard to overlap an x orbital on one atom with a y orbital on another, because then all you did was change the nomenclature. So again, x with x, y with y, A with B. So hopefully this should make some sense. And what's more or less going to be happening is I'm going to bring these two atoms closer together. And when I do so, I'm going to build up an overlap with increased density in the middle, which, however, as we've seen before, means we need to play around with our normalization constant, as it depends on the overlap integral. So when we do this, we're going to have a normalized symmetric combination of our two atomic orbitals. But as usual, we like describing these systems with inversion symmetry, mostly for historic reasons, which gets a little bit troublesome in this case. Because when I'm talking about sigma bonds, the bonding orbital has Girard or even symmetry. In this case, it gets a little bit messy, because all of my positive amplitude is on one side of the molecule and all my negative on the other. This means if I try and project a point through the center, stays the same magnitude, flip sign. Our bonding pi orbitals have Ungerad symmetry, so we're going to represent it with pi u. So again, something to watch out for. However, as we move our way to anti-bonding orbitals, where now I've flipped the direction, so there is a push against each other because my phase of my wave functions are out of alignment. However, that makes it perfect for inversion symmetry. So my anti-bonding orbitals went from Girard in sigma bonds to Ungerad in pi bonds. So our anti-bonding orbitals are again going to be a normalized anti-symmetric combination of our px or again our py orbitals. Can work for either. For convenience, I just dealt with one. So again, this is actually a fairly useful notation, but nothing should be too surprising in the construction of the wave function. But again, don't forget that now our bonding orbitals have Ungerad symmetry and our anti-bonding orbitals have Girard. So again, I apologize. This is a fairly common convention still, and because of that, you have to be aware that we have one symmetry convention for the sigma, and it flips as we go to the pi. So make sure you're aware of that as we progress. But I'm an energy guy. I want to care about the exact form and shape of these interactions. And as we've seen before, this is largely driven by the extent of overlap in between my orbitals. And we're going to expect overlap to be a good thing for bonding orbitals and a bad thing for anti-bonding, because as stabilized as this species will be by bonding, by overlap, this species will be equally destabilized because all the overlap moves to the outside. So let's take a look at our overlap integral, because of course we managed to have a pre-solved one for this guy too. And just like with the sigma bonds, we've made this a general form that depends on the charge of the atom and the radii of the system. And again, because I'm doing with a two and a second shell orbital, I'm going to have a exponential die-off with the wave function with regards to charge and radii. So the wave function will die off a little bit slower than for a first shell, a little bit faster than for a third shell. And because of that, the overlap will reflect this same idea, just amped up a little bit because now I've got the decay of two separate atoms to account for. So again, the actual shape is dealt with our polynomial function. So in this case, it is worth noting that all of our terms are positive, which means that we are going to show a constant positive overlap integral. And because of that, this term dominating at large radii, distances between atoms, we're going to see a constant exponential decrease with a little bit of extra shape added by the overlap of these two functions. Again, if I bring them really close, they'll be directly overlapped, and it doesn't get better than that. Just turns out our nuclei hate it. But as I end up extending the distance between the systems, our die-off actually is going to be fairly slow at the beginning because most of our function will still overlap. And then as I go on, it dies off fairly quickly until I have this constant slow exponential decay. And it turns out we can indeed see that when we plot our overlap integral versus our internuclear distance, which we built in charge for convenience here because our charge and radii tend to come together. So when we do this, we see more or less a damped exponential function with a slow decay going down at large distances. So again, distance gets large enough. I've got no real overlap. Bonding characteristics fall apart, both in terms of bonding, but also in terms of anti-bonding. So depending on our system, that can be important. But it is worth noting that we want to go ahead and compare this to the sigma bonding in between p orbitals, which should be happening at the same time. And I do want to remind you that with the sigma orbitals, if they get too close, so if I have another sigma set here, it gets too close, I can start having overlap in between the positive and negative. And so if I've got my two atoms occupying the same distance, turns out my overlap isn't bad, it's really bad, as in all negative bad. And so you need to be within a certain distance for the two p orbitals to have a good set of overlap, which is again what we're seeing here. So do not expect many bonds to form at internuclear distances less than this, because at this point we're fighting against overlap, not with overlap, which can be slightly problematic. But as I extend the distances, what ends up happening is I hit this maximum level of probability density where my two positive lobes in between my p orbitals perfectly overlap. So this would be ideal. In truth, we often will sit somewhere in here where I'll have the nuclei just sitting out far enough so I get decent electronic overlap between the two systems, but not perfect. But it is worth noting at this point, it turns out that my overlap for my sigma bond is much better than my overlap for my pi bond. This is a very important consequence because under these conditions, my sigma bonds are able to reach past the pi bond much better because this pi bond with its oblique overlap isn't going to be great. Whereas this direct overlap for the sigma bonds, it can reach out a little bit further, is going to maintain larger overlaps at further distances. And as a result, we tend to see that sigma bonds are going to be a little bit more stable than the respective pi bonds. And again, it's mostly being driven by this overlap idea. So what we can do is start taking into account what we know about overlap in between our p orbitals forming the sigma and pi bonds and use them to order the relative energies. So we're going to start by assuming that we're going to have relatively reasonable equilibrium separations, which are going to be more out in this region. And using the overlaps as a proxy for good connections and good bonding character, what we're going to find is that we can use this to relatively order the strength of our bonds. So the sigma bond generally is going to have the greatest overlap at reasonable bond distances. But this has two very important consequences. The first of which is that my bonding orbital is going to be the lowest in energy, because high overlap means good bonds. But if something goes down, something else has to go up in the MO world, which means that if my bonding orbital goes down, my antibonding is going to go up at least as much, probably a little bit more. And so when we do this, while my bonding orbital is going to be low in energy, my antibonding is going to be really hard to get to. Now, the overlap in between the pi bonds isn't as good, which means it won't go as low, but nor will it go as high. So my two pi orbitals are going to form a degenerate set, because I'm going to have two bonding orbitals at the same energy and two anti-bonding orbitals at the same energy. And neither one of these are going to be mixing because they're pointed in opposite directions. But the bonding are going to go down a little, the anti-bonding going up a little, but they're not going to rival the sigma bonds in either direction. And when we put this all together, what we start building is a basic form of an orbital diagram that you might be familiar. I take two sets of p orbitals, so I've got 3 orbitals in here. So my 2pz will mix to make my sigma bonding, which goes way down, my sigma anti-bonding, which goes way up. So that's how we end up forming the lowest and the highest energy species. But that remaining X and Y are also going to mix to form 2 identically energied species down and 2 identical energied species up. So again, one of the things you should watch out on these orbital diagrams is because it can be a little bit hard to show 2 energy levels, what they'll often do is stack them. So despite what it looks like, they do not have different energies. They are exactly the same. It's just hard to portray that. So they want to show that there's 2 levels more than they want to show that they're at the same. But something for you to be aware of when you're looking at these diagrams. So I brought in 6 orbitals, 3 p orbitals on B, 3 p orbitals on A, and I get 6 MOs spread out. 3 low energy bonding, 3 high energy anti-bonding. The one that's the lowest tends to also be the one that's the highest. Now, this will break down later when we work with messy systems, and that's because it's possible for these orbitals to mix a little bit with the guys we forgot about, S. So let's take a quick moment to look at how my various p orbitals, my p atomic orbitals, can interact with my s atomic orbitals and what this might mean for MOs. So how can I modify my MOs by bringing in the S? So the first one that makes kind of sense is we want to look at that S and that PZ orbital, because both of these can do direct overlap. And it turns out that these 2 can actually interact. So one of the things you have to watch out for is that your 2s orbital may end up interacting and modifying the energy of your 2p orbitals. So this means that these 2 sets of sigma bonding and anti-bonding may actually have a significant degree of interaction, and this will play a little bit of havoc with our MOs later. But it's also worth noting that this process is going to be very sensitive to both the charge and the distance between the nuclei, because the greater the charge and the greater the distance, this essentially means the less overlap I'm getting. And my s orbital, which is much bigger, is going to prefer to interact with something that's bigger and more spread out. Because if these guys get sufficiently spread out, this S is spending a lot of time up and a lot of time down, and same thing in the both in the direction in and out of the board. So when we do this, the overlap isn't going to be nearly as good as with something that has a similar shape. So if I've got systems that are fairly far apart, the S is going to definitely overlap much better with something that's as diffuse as it is. But if my charge is weak and I've got a short distance, then as you noticed here, I can get some pretty significant overlap in between this S and P orbital, and it can play a fairly significant role. So one of the things you should watch out for is that you may see some mixing if you've got light atoms with short distances, which often come together. So when we do this, one of the other things you should watch out is how the PZ or PX and PY orbitals may also interact with, say, an S orbital. Well, what ends up happening here is an S orbital is all positive amplitude in its wave function. The X is a mix of positive and a negative. And the S and its relative, the PZ orbital, are going to be coming at a right angle, which means that positive amplitude is going to have an even mixture of the positive interacting with the positive and the positive interacting with the negative. So this is a constructive overlap, and this is a destructive overlap. But more importantly, because this is a right angle, they are exactly equal. So you have equal constructive and destructive overlaps. This means they cancel out. And because of how we end up adding these things together, it turns out this gives us an overlap integral, or S, of 0. And if you don't have any significant overlap, it means you're generally ignoring each other. So this is one of the reasons why we can say that I can treat my PZ and S orbitals together, and then my PX and PY acting on their own, and I can treat everybody separate. Because it's not that they interact, it's they interacted in a way that just doesn't matter, because all effects end up canceling out. So this is one of the reasons why we can do this separable set of functions. And as we've seen anything this semester, if I can separate things out into easier to solve problems, that's great. So next time, we're going to be taking what we now know about the relative energies of the p orbitals, how they interact with the s, and we're going to bring this together to finally make a real MO diagram. Take care out there and stay healthy.